So just notice that the nucleophile substituted the place of the leaving group, right?
Mm-hmm.
So it's very simple. Nucleophile attaches, leaving group leaves, and this is for the basic condition. Okay, now let's look at the acidic condition. Alright, so what we're saying is that we're still going to get the nucleophile come in, the leaving group leaving, but it's going to be sandwiched between protonation, deprotonation, protonation, deprotonation, right? And we could take a quick example of this. Alright, so if we start off with this, the leaving group, some random carboxylic acid derivative, we're going to react it with a nucleophile, right? And it's going to be an acidic condition. First thing that happens is the carbonyl oxygen gets protonated. So this guy here gets protonated. So this is going to be in equilibrium. We'll generate this guy, positive charge here, leaving group here. We're going to get resonance. Right?
Mm-hmm.
And now this, so once we protonate the carbonyl oxygen, then the nucleophile comes in. Right? So we protonate the carbonyl oxygen, nucleophile attaches, and the nucleophile gets deprotonated. So this is our nucleophile now, it gets deprotonated, and we'll just assume there will be some base in here, right? Whatever gets deprotonated here, we'll use the conjugate base of that to deprotonate this. Cool?
Mm-hmm.
Now what's going to happen? So we get protonation, nucleophile attaches, nucleophile gets deprotonated.
Then this has to be deprotonated. Or sorry, the leaving group leaves, and then that gets deprotonated.
That's right. So, but before, okay, so we get protonation of the carbonyl oxygen, nucleophile comes in, deprotonation of the nucleophile.
Oh, then protonation of the leaving group, then
Perfect.
Leaving group leaves.
So this guy gets protonated. For the most part, that's what's going to be happening, and then we will have leaving group, positive charge, nucleophile, and this swings down, the leaving group leaves, positive charge, nucleophile here, and there will be some base in solution. This guy gets deprotonated, the carbonyl oxygen gets deprotonated, we'll be left with our product. Alright, so now notice that in both of these cases we're forming the same product. Right, so this here is the same thing as this here. So most of these reactions are going to be occurring in basic or acidic condition. The basic mechanism is a lot simpler because it doesn't have all the protonation, deprotonation. Right?
Mm-hmm.
Alright, so we said that these guys are called the carboxylic acid derivatives. Do you remember why they were called the carboxylic acid derivatives?
Because something like they can always make a carboxylic acid.
That's right. So all of these guys can make a carboxylic acid. And do you remember the name of the reaction that produces it?
Hydrolysis.
That's right. So let's call this H1. Let's call these guys H2s. right? So we can do a hydrolysis. So we're going to say that H is going to represent hydrolysis. And we'll say that H1 is H2O. And we'll say that H2 is H2O, either in acidic or basic condition. And sometimes you might see heat. Right, so it can occur in acidic or basic condition. So all of these guys can be hydrolyzed back into the carboxylic acid. Now, because these two are more reactive, they don't really need the acid in the base. You can just drop in H2O and you can get the hydrolysis to occur because they're really reactive. But once you get down here, these guys are going to need more like prodding. So you're going to need acid and heat to react them. And am I forgetting a carboxylic acid derivative on here? Acid halide and hydride.
Let me check.
I think we have all of them. No, that should be all of it, right? Okay. So what we want to actually do, we want to relate a lot of these reactions so you have it. And if we had more time, we can work on synthesis of these guys so you can see how you would see it on the exam. But let me quickly cut this guys out. Yeah, I copied it by accident. It was unintended. Cool. Okay, so now, so who's the most reactive out of all these guys?
The acid halide.
Okay, perfect. Now, the way the reaction occurs, the substitution reactions is going to be occurring is that whatever is upstream here, so we'll say this is upstream, this is downstream. From upstream we can get everything downstream, but we can't go back upstream. So from here we can get this, from here we can get this, from here we can get this, from here we can get this. And this guy is weird. The nitrile is weird. So we have to get this guy indirectly. So we want to like make a broad relationship so you can see how a lot of this stuff is working, and it will help you on the synthesis. So from here we can make everything here. From here we can make everything here. From here we can make everything here. From here we can make everything here.
Okay.
And then this guy is just weird.
Okay.
So now if we start with this acid halide, all we have to do is drop in the nucleophile, right? Because this is going to be our leaving group, right? We drop in a nucleophile that will replace this so we can form the anhydride.
Okay.
Do you know what that nucleophile would be?
This.
Perfect. And we'll just say, like in basic condition, you'll see it as a salt. Or you might even just see it like this. Either way, you should know what's going to happen, right? And in this case, we're going to put this in pyridine. And the reason why we're going to put this in pyridine is because we're going to form HCl, and this soaks up the HCl. And we can produce the carboxylic acid, and that one is simple by the hydrolysis. What reagent do we use?
H2O.
That's right. And we can produce an ester. What reagent do you think we would use to produce the ester?
OR.
But it's going to be it's going to have a
H.
That's right. So this would be an alcohol. Right, and then we do pyridine. We can produce an amide. Do you know what reagent we would use to produce the amide?
NH3.
That's right. Now notice that in this case here, okay, so in this case here now, there can be a different amide where we can have a carbon chain sticking off here. So whatever it is, you should be able to determine by the nucleophile that comes in, right? And then we can't directly get the nitrile from the acid halide. Cool? Alright, now if we start off with the anhydride, we can form the carboxylic acid. You know how we would form that?
H.
That's right. How would we form the ester?
ROH.
That's right. And this time we don't need a pyridine because we're not forming HCl.
Okay.
How about the amide? How would we form the amide?
NH3.
That's right. And then we can directly form this guy. If we start off with the carboxylic acid, how can we generate an ester?
ROH.
Perfect. An acid. Now, notice that with these ones, we're not really using acid with the anhydride because they're really reactive. But once we get down here, we're going to be using a acid or heat. Right? We're going to start using acid or heat when we get down to these guys because they're not all that reactive, and we want to force the reaction to occur. Now, just want to jog your mind a little bit. You know what reaction this is?
Fisher's reaction.
That's right. All right. Now from here,